Section 6.4, problem solving. Let's start with the following warm-up problem. Let f of x equal -3 times x plus 4 squared minus 1. We're first going to determine the coordinates of the vertex. Note that our quadratic function is in vertex form. The benefit of vertex form is that we can immediately tell what the coordinates of the vertex are. For the first component of our vertex, note that we're adding 4 to x inside of the square. This means h in our vertex form is equal to -4. Because remember, vertex form has x minus h inside of the square. Since I see +4, that means h should be the opposite sign, which is -4. What I'm adding and subtracting outside of my square tells me the value of k, and since it's plus k outside, we keep the same sign for k. So our vertex is the point -4, -1. Next, we're going to write our function in standard form. Standard form is the ax squared plus bx plus c form, where our quadratic function is in the simplest form we can make it. To start, we'll expand the x plus 4 squared. Now, there are two ways we can work with the x plus 4 squared. We can use the following special multiplication rule. This comes about from the definition of squaring, where when we square a number, we're multiplying that number to itself, and then from there, we could FOIL. You could either write the x plus 4 squared as x plus 4 times x plus 4 and FOIL, or you can use the special formula we have written. For this problem, I am going to use the special formula. So when I apply the special formula to the x plus 4 squared, we get x squared plus 8x plus 16. Note that I have the x squared plus 8x plus 16 in parentheses. That's because I still have to multiply this expression by -3. So now I'll distribute in the -3, and I can drop the parentheses. Then I can collect my like terms, which would be the -48 and -1. And we get -3x squared minus 24x minus 49 as the standard form of our quadratic function. If you wanted to check to make sure you were correct, notice how the leading coefficient, -3, still remains the same. Second, if you use the -b over 2a to find the x coordinate of the vertex, -24 divided by -3 times 2 does give us -4. And if we plug -4 into our function, we do get -1. So the vertex still remains -4, -1 in our standard form. You could also check with Desmos, graph both functions, make sure both graphs line up. That would also be another way to check as well. We've already seen quite a few different problems that use quadratic models. Let's summarize what we've done in those past problems to create a strategy to help us with solving problems moving forward. After we've read the problem, the first thing we want to look for is any information in the problem that implies the value of one of the variables. If yes, then we plug the value in the variable and we solve for the other variable. Now, depending on the situation, the verbiage may change. For example, if it's a problem involving height, we may want to look for terms like, what is the initial height? In that case, that tells us time is 0. Or they may want to know when the object hits the ground, in which case the height is 0. Or in area problems, they may tell us a specific area we want dimensions for. It does vary depending on the verbiage. The second thing we want to look for is the problem asking us for the minimum or the maximum value of the dependent variable. Well, whenever we're trying to find the maximum or minimum of the dependent variable, we're going to associate that with the vertex. One of the special characteristics of a parabola is that the parabola has a highest or lowest point. So it does allow us to figure out maximum values of a model. So always read your problem very carefully, trying to identify one of these two scenarios. That way we can solve the problem accordingly. We've already taken a look at quite a few problems where quadratic models were used for geometry and height-based problems. Now we're going to take a look at how quadratic models can appear in business. The next few problems we're going to discuss in this section involve revenue, cost, and profit. We're going to let x be the number of items of a particular object that is for sale. The revenue, which we're going to denote as the function r of x, is the amount of money that you obtain for selling the x objects. The cost, which we're going to denote c of x, is the amount of money that you must spend to make the x items. And third, the profit, which we're going to denote p of x, is the difference between the revenue and the cost of the x items. Now, how can we calculate the profit if we know the revenue and cost functions? Well, just from the definition, p of x equals r of x minus c of x. If p of x is negative, in other words, you have a negative profit, that does indicate a loss of money. This occurs when the cost is greater than the revenue. If p of x is positive, then you made money. This occurs when the revenue is greater than the cost. And thirdly, if your profit is 0, this means you broke even. Breaking even means the cost and the revenue were exactly the same. You didn't lose money, but you didn't make money. A company's revenue earned from selling x thingamajigs is given by the function r of x equals 200x. The cost to make x thingamajigs is given by the function c of x equals 1,400 plus 1.2x squared. The first part is we're going to write a function that represents the company's profits when x thingamajigs are sold, and this function is going to be called p of x. Recall that p of x, profit, equals the revenue minus the cost. So p of x equals r of x minus c of x. R of x is the 200x, and our cost function is 1,400 plus 1.2x squared. Notice how I have parentheses around the cost function. This is because we have to subtract the entirety of the cost function from the revenue. If I don't have parentheses, then it looks like I'm only subtracting 1,400 from our revenue. To simplify, we'll distribute the negative into the parentheses, and at the same time, I'll rearrange the order of the terms. And we get that the equation for our profit function is negative 1.2x squared plus 200x minus 1,400. How can we check to make sure the equation that we got for profit is correct? Going into Desmos, I can enter in both the revenue and the cost functions. And for this, because I'm only concerned with the profit, I'm going to turn off both graphs. in the next line, I can use the function notation to write how we would calculate the profit function. That is, P of X equals revenue minus cost. And notice we have a line here in green. Now below it, in line 4, we can enter the equation that we got. Now to avoid confusing Desmos, instead of using capital P, let's use lowercase p. And there I have my equation entered. And notice how the green and the purple overlap. And if I zoom out a bit more to see more of the graph, now I see the two purple parts, and you can see the purple and the green perfectly overlap, indicating I did find the right equation for my profit. Next, we're going to find and interpret the vertical intercept of P of X. The phrasing vertical intercept is another way of saying we're trying to find the y-intercept. But because we're technically not using y, it's better to say vertical instead. But either phrasing, we know that we have to set x equal to 0. And since we're trying to find the vertical intercept of P of X, we're going to plug 0 into our P function. Since we already have our profit function entered into Desmos, I'm going to delete the line where we have the equation that we found in the first part, and we're going to enter P of 0. And Desmos evaluates that for us. And we have P of 0 equals negative 1,400. This is much quicker than us having to zoom out and play with the graph. But if we want to check, we at least now have an idea of where it should be located. And we can see the intercept highlighted for us, the point 0, negative 1,400. So how would we interpret this? The x equals 0 indicates that they didn't make and sell any of their thingamajigs. So if no thingamajigs are made and sold, then, well, P of 0 being equal to negative 1,400 tells us we lost $1,400. So the full interpretation, if no thingamajigs are made and sold, then the company will lose $1,400. Notice I did not say lose negative $1,400. Putting the term lose indicates that my profit function was a negative value. Next, how many thingamajigs must be sold to maximize the company's profit? What is the maximum profit? Since we're referring to the maximum profit in this problem, this tells us we're looking for the vertex of our profit function's graph. How do we know the vertex is the highest point? Since A is negative 1.2, which is a negative value, we know our parabola opens downwards, which means our vertex is the highest point, which means our vertex would indicate what the maximum profit is. Now, as for the how many thingamajigs must be sold, that's referring to the x-coordinate of the vertex. Now, we could scroll through the graph, but we do have a nice little formula that will tell us what the x component of our vertex is when our quadratic function is written in standard form. That is x equals negative b over 2a. Going to our profit function we found in the first part, a is negative 1.2, b is 200, and c is negative 1,400. Going into Desmos, we can type in our formula with the values plugged in, and we get that negative b over 2a with the values plugged in is 83.333, and we're going to round to the nearest item, which is 83. Because of how the parabola is shaped, we could either round to 83 or 84, depending if you want to round up or round down. But the reason why we want to round to 83 in this case, following our standard rounding rules, is because 83 is closer to 83.33 than 84 is. So the point where x equals 83 will be higher on the parabola than the point where x equals 84. Now that we know how many thingamajigs must be sold to maximize the profit, what is the maximum profit? To find what the maximum profit will be, that is the second component of our vertex, which means we're going to take 83, plug it into our profit function. Going back to Desmos, we'll just type in P of 83. And we get that P of 83 is $6,933.20. If we do want to confirm this is correct, or if we do want to use the graph, we would just have to zoom out and move the graph around. Since we know it opens up, we would scroll upwards from where we were. And if we trace onto the gray dot, we see that our vertex is 83.3 repeating, 6,933.3 repeating. Now, because of the rounding, our answers won't be exactly that. Instead, we rounded the x to being 83, and it caused our profit to equal $6,933.20, which is still close to the $6,933.33 we see here in the vertex. Only a 13-cent difference, but this difference is due to us rounding to the nearest integer. Next, we're going to find what is the minimum number of thingamajigs that must be sold in order to make a profit. So we're trying to figure out the first instance of when our profit will be positive. We're going to start by finding the break-even point, which is when P of x equals 0. The break-even point recalls where we don't make any money, but we didn't lose any money. So this would help us get started to figure out when we first start making a profit. So when we set our profit equal to 0, we're trying to solve the equation 0 equals negative 1.2x plus 200x minus 1,400. Because our function is in standard form, we're going to want to use the quadratic formula, which recall from the last section is negative b plus or minus the square root of b squared minus 4ac all over 2a. We've already identified the values of a, b, and c when we were trying to find the maximum profit. In Desmos, we'll just type in what our formula would be and replace the variables accordingly. And there is my quadratic formula typed in for the plus, and we'll copy and paste for the minus. So there are two instances where we break even. We break even when we sell 7.32 thingamajigs or 159.34 thingamajigs. What is the minimum number to make a profit? Meaning we should look at the smallest break-even point. Well, the smallest break-even point would occur when x equals 7.32. But the question becomes, how should I round the 7.32? If we go by our normal rules of rounding, we would want to round this to 7. Well, if we evaluate P of 7, I get negative 58.8. But if negative 58.8 is negative, does that indicate us making a profit? No, it indicates a loss. So instead of rounding to 7, we're going to round up to 8. So when 8 thingamajigs are sold, that is when we first make a profit. That's because at x equals 7, we're still losing money. So what is the minimum number of thingamajigs that must be sold to make a profit? 8 thingamajigs must be sold in order for us to make a profit. I own a hotel with 1,000 rooms. When I set the price to stay in one of my rooms to $200 per night, every room is booked. I estimate that if I increase my price by $1 per night, then the number of booked rooms decreases by 2. First, we're going to determine a formula for the revenue, R, I will yield in terms of X, where X represents the increase in price. Recall that revenue is the amount of money we're bringing in for selling items. The way I can calculate revenue in this problem is that the revenue will equal the number of rooms booked times the price per room. So with that in mind, let's focus on those two aspects. Well, in the problem, we know what the initial price per room and how many rooms were booked at that price. If the price per room was set at $200, all of our rooms were booked. Well, my hotel contains 1,000 rooms, meaning all 1,000 rooms were booked. But now we have to think about what happens if I change the price. I'm told we're letting X represent the increase in price. So we're adding X to the 200 to represent the new price per room. So the new price per room will be 200 plus X. But we're told in the problem that for every dollar I increase my price, the number of rooms booked decreases by 2. So if I raise my price by X dollars, the number of rooms I'm going to book decreases by 2 times X. If my price per room is 200 plus X, the number of rooms booked is 1,000 minus 2X, which means my revenue, which we're going to make a function R of X because it does depend on X, is going to be the product of those two expressions. So our R of X equals 1,000 minus 2X times 200 plus X. And there's my revenue function. Next, what should I make the price of a room per night to maximize revenue? Well, going into Desmos, let's type in our revenue function. So now we have our revenue function typed in, but I don't see the graph quite yet. Now, instead of just zooming out wildly to try to locate it, let's think about what the zeros should be. If we look back at our function, we see that it's factored. If I set my factors equal to 0, I know my x-intercepts are going to be negative 200 and 500. The negative 200 comes from setting the second factor equal to 0. The 500 comes from setting the first factor equal to 0, and solving for x in both of them. Since they're referring to the maximum revenue, we do want to try to find the vertex. To find the x component, we'll average our two x-intercepts, meaning we're going to add the two x-intercepts together and divide them by 2. And when we do, we get the x component of our vertex is 150. Do I need to know the y component of my vertex? No. They're asking, what should I make the price per room to maximize the revenue? They didn't ask us what our maximum revenue would be. So my revenue will be maximized when x equals 150. But the 150 still does not answer the question. They want to know specifically what is the price per room. Well, if we think about what the x component represents for any point on our graph, the x component represents the increase in the price per room. So our actual price per room, using what we've talked about before, that the price per room should be 200 plus x, will be equal to 200 plus the 150, which means we should set the price per room to $350 a night to maximize the revenue. If we do want to check that we got the correct x, we can go through the graph with our revenue function typed in. We get that our vertex is the point 150, 245,000. 150 representing how much I should increase my price per room. 245,000 would represent what my maximum revenue would be.